So these rational functions, when we start graphing them, they're going to have sort of all sorts of weird different behaviors that polynomials didn't. And it's because of that, the division of, yes, the division of some expression that has x in it. It's going to create all sorts of kind of kooky things going on. So the most predominant feature in these functions is that a lot of the times they'll have what's called a vertical asymptote. So on a graph, this is a feature where the curve starts looking more and more vertical, or more and more like a vertical line. So I've just drawn some examples of what we've got here. In each of the example, you'll see this red dotted line. A dotted line on a graph is sort of like those open circles on a graph. It's something that's not really there, but it's to be used as a guide for things that are near it, right? Like an open dot is the absence of a point, but it tells you where a curve is going. And that's sort of what this dotted line does. So the dotted line are not points on the curve. They are a guideline for this feature. And if we look at the graph here, close to that dotted line, we get the left and the right side of this blue curve. And what we can see is that it starts going up and getting closer and closer to that dotted vertical line. And on the left side, it's not quite as close, but it is doing the same thing. And even if there's no arrows in the picture, if it just sort of goes off of the outside of the graph, you would assume that your blue curve will keep going predictably. And that dotted line tells you what to predict. It uses that dotted line as a guide, so it'll get really close to it. So in the first graph, we have one vertical asymptote, and that's that dotted line, but two parts of the curve are actually going to use it. So it uses it on both the left and the right side. On the second curve, you can see that on the right, the curve starts to go almost straight up along that vertical line, and it's also doing it on the left. It's going almost straight down towards that vertical line. And then finally, this last one is a little bit of a weird function. We can see that it's doing it on the left. It's using that red dotted line and sort of going straight up. On the right, it's not using the vertical asymptote. So this feature here is not something you'll see in a rational function. So rational functions will use both sides of the asymptote, as we have in the first two examples. We could maybe use a piecewise function to describe what's going on in this third one. But where maybe like the left piece is rational and the right piece is linear, but this is not a behavior of a normal rational function. So they'll always use both sides, and they'll either both go up, both go down, one goes up, one goes down, or vice versa. So this is typically what vertical asymptotes are going to look for us. You'll see a lot of things that look like examples 1 or 2 here. Yeah. Okay, so where we're going to find these vertical asymptotes in rational functions, it's pretty easy. What we'll see is that we're going to get these vertical asymptotes when, again, after simplifying, just like finding the zeros, the denominator, the bottom, is equal to 0. So I'll go through the first one. Just f of x is 1 over x in pretty thorough detail, mostly because I think we know the bottom is 0 when x is 0. What I want to do is explain why we get that feature here. So obviously, yeah, I know x equals 0 works. So what I'm going to do is let's plug in some numbers close to 0. So let's do maybe like a table of values here, which you wouldn't have to do in practice, but this is just to explain why we're getting what we're getting here. So what I'm going to do is, let's say x and f of x. So let's plug in some numbers. 1 is pretty close to 0, but I want to get really close to 0. So like 0.1, 0.01. And then what I'll also do is some numbers on the other side of 0. Let's plug in some negatives. So if you have seen any calculus, this is very much the idea of what a limit is. I'm taking numbers closer and closer to 0 and evaluating what happens. So if we plug these in, I'll get f of x is 1 over 1, which is 1. 1 over 0.1, which is 10. And then 1 over 100th should be 100 if I plug that in. I know that 1 over 0 does not exist. And then these are going to be 1 over the negatives of the one before. They'll just be negatives. So negative 100, negative 10, and negative 1. So if I were to try to graph this, it's not going to be great because I'm not going to be able to really get that scale of all the way up to 100 on here. But I can maybe get up to 10. Let's say that's 5. Remember I said I'd only label it if I wasn't counting by 1. So as you can see, I'm not counting by 1 there. So I'm going to actually label it for myself. And yeah, let's plot some points. You'll see we have 1 and 1. So if this is my 1 on the right, then 1 is about 1/5 of the way up there. And then that 0.1 is going to be really close to the y-axis and then all the way up here at 10. If I want to plot a couple more points to really see what's going on, if I had 2, it would be at 1/2, so it would get a little bit lower and lower. And that's something else to discuss later. But what we can see is that as it's moving over, it's going up like this. And then the next point is even closer to that vertical, but much, much higher. It's all the way up to 100. So it's going to look something like that. And basically, we could say that it's using this vertical line at x equals 0. That's the equation of this dotted line as a guide. And then similarly, we get the exact opposite on the bottom. If you remember, this is actually an odd function. So we are going to get pretty much the same behavior down here. And it looks something like that. And it's using the left side of this vertical line at x equals 0. Remember, vertical lines always have the equation x equals something. And so we can see that behavior here. So that's my vertical asymptote. I'll just use VA for that. Yeah, but that's what happens when we plug in something that makes the bottom close to 0. It means that we're dividing by something very, very small. And when we divide by something really small, it actually makes the number bigger. So it kind of blows up and it gets this like infinite height to it. And that's where vertical asymptotes come in. So we'll look at the second one, simplifying the denominator 0. So for this one, I'm just going to maybe kind of go ahead here. The top doesn't factor, similar to the question in the last video. It's x squared plus something. So that won't have any roots because this thing is always greater than 0. The bottom does factor, however. So we should get x squared plus 5 over x, and I believe that's actually minus 3 squared. So we're going to get our vertical asymptote when the bottom is 0, which would be when x minus 3 squared is 0, which is at x equals 3. And so again, just kind of the logic here, I'm not going to go through as much detail as I did with the previous question, but if we're near x equals 3, the top is approximately 14, right? 3 squared plus 5. Like even if it's 3.1, the square will make it maybe a little bit larger, but it's pretty close to 3 squared plus 5 equals 14. The bottom is very close to 0, or 0 squared, if you will. But what we're doing is now doing 14, which is a moderately sized number, something really close to 14 broken into tiny, tiny parts. There's lots of those parts. And that's why we're going to get sort of really high values, really infinite-ish values near that x equals 3. All right, so we're going to kind of whip through the last couple. Again, I'm going to factor everything. The bottom should factor to x minus 4, x plus 1. So again, we're going to pay attention to this after simplifying, because those are just going to wipe each other out, those x minus 4s. And so we're actually only going to get that vertical asymptote at x equals -1. And then for D, same thing. What is that, k of x? I don't know what letter I'm going for there. Let's say it's k. Again, factor the bottom. You'll notice in this case, the bottom actually factors to x plus 2 squared. We will get a little bit of cancellation here, but it doesn't wipe out everything on the bottom. We still have an x plus 2 left on the bottom, and that is actually going to be okay. That is going to give us a vertical asymptote at x equals -2. So the reason why, when we were considering zeros, if there was anything on the bottom, then it, yeah, if it made the bottom 0 in any capacity, it couldn't be a 0 because it's undefined there. With these rational functions, the function won't be defined at that dotted vertical line. It skips over that dotted line, so it should never be part of your domain. And so, yeah, you can have a vertical asymptote even though you wipe off a factor from the top if there's more factors on the bottom. Yeah, so that would be vertical asymptotes, and we're going to look at some horizontal ones next.